Another circular motion problem. This one specifically deals with things going in a circle, specifically upside down. Uh, so we're talking roller coasters. If you're spinning something on a string, all those situations. The train video here and Hot Wheels track video, I would encourage you to just Google those. They have live. Um, I shouldn't say it's live. Real versions of Hot Wheels cars that go around these tracks. It's just cool to see. But we're going to calculate. The question is, well, this question in specific is how much force do you feel? But we can also calculate how fast you have to go to not fall off these coasters that go upside down, or anything that goes upside down for that matter. So, how much force would a 65 kilogram rider feel? So we're looking for the force you would feel is what we would call the normal force. That's you interacting with the track. The radius of these curves is about, again, that's my awful R, but that's 25 meters. And you're traveling around 15 meters per second. Now in parentheses, I put R units. So it's typical, so it's about a 140-pound person going 34 miles per hour. I did not put 25 meters in R units for some reason. But anyway, um, typical average roller coaster, you're just going upside down in a circle. So top of that, we got different locations. Obviously, I'm gonna do top of the hill with you. I'm gonna calculate that one completely, and then I will, like it says, just discuss the equation for the bottom of the loop, and then I will leave the top of the loop for you guys to do on another slide. But how much force would the rider feel top of the hill? So you're right here. So like all force, this is a force problem. So you're starting with sigma F equals ma. Now these are always going to be the same. You're on a surface. Sorry, before I get there. We're going in a circle though, a circular path, so we're going to subscript these as centripetals. So then like all force problems, we ask ourselves, well, what forces are causing us to accelerate? But this one specifically accelerate in a circle. So we're only talking about the forces that are causing us to go in a circular path. So, well, here's the center of the circle. We definitely got gravitational force pushing us down. The track is pushing us up at a normal force. So there's our two forces. Track pushing up, so I'm going to call that Fn. And then what's pushing down on us is Fg. These two together are giving us the centripetal force. The centripetal force by itself is not a force. It's due to other forces. Circular motion forces are due to other forces that we've already talked about. So normal force, gravitational force, one's up, one's down, so we subtract them, equals MAC. And then we're going to do one more thing before we start plugging in numbers. If they had just given us AC, I would start putting in numbers now, but they did not tell us what AC was. They also did not tell us what Fg was, but we know Fg is mass times gravity, and we know AC is V squared over R. So we're just going to make some changes so now we can just plug in numbers. Fn is what we're looking for, so you leave that alone, minus the mass, which we said, I did not write it down, sorry. Here, I'll add it now. Mass was 65 kilograms. So 65 times, now I'm not making this 9.8 negative because I already said it was down. I already said it was negative. So I'm going to leave that alone. Equals 65. Now what's my velocity? I was going 15 meters per second, so I square that, and then I divide by the radius of 25. Now here's where we got to pause for a second. What direction is AC? Well, AC always points to the center of the circle. So if the center of the circle is beneath you, then this is negative. That whole V squared over R is negative. So when I type that in the calculator, I need to make sure I got that negative sign. I'm going to do that now for you guys. Just pause for a sec here. So we do that, and we get Fn equals 52 newtons. And so if we do convert that to pounds, we multiply that by 0.225 pounds in a newton, and then that's where I'm getting the 12 pounds from up in the answer up here. Which just means, and you've all experienced this, go over a hill you feel lighter. The car is actually throwing you out of your seat for a split second, and you're leaving the seat. So if you were sitting on a scale, as weird as that sounds, is as you leave the scale, the weight would go down, and you would decrease your weight to you'd feel 12 pounds. If the average person 140 pounds, then that person would feel 12 pounds at this particular 34 mile per hour over this particular curve. Sorry, obviously it'll vary for everything, but that's the idea with that one. So that is the top of the hill. For the bottom of the hill, I'm just going to squeeze this in down here. So that was part A. Part B wants to know Fn at the bottom, bottom of the loop, or the bottom of the hill. I guess it's the same thing in this case. Fn's question mark. So it's the same question as above. The radius, mass, velocity all stay the same. Situation's a little different. Now the center of the circle is above us. Force-wise, though, it's still the same. Fg is pushing us down. The track is pushing us up towards the center of that circle. So it's still Fn minus Fg equals MAC. The only thing that's going to change is what's... so Fn minus Fg, that stayed the same. So that'll be identical to what we did above. AC, again, is V squared over R. And we got to ask ourselves, which way is AC? So is AC positive or negative? That's the question right now. Well, you just look at the picture. The center of the circle is above us. So AC is going to be positive for this one. And then you'll feel, again, last time you bottomed out. Now, this could be a coaster or just driving in your car. But when you bottom out on a hill, now your body wants to keep going down. And again, if you were sitting on a scale, you would feel heavier. We've all experienced this, but that's what's going on with these types of problems. Same thing if it was something on a string, like you're spinning something around like a sling. Then instead of Fn, instead of normal force, we would look at the tension force. But I'm going to leave that top part of the loop for you guys.